Our planet may be under threat. One day, a natural or man-made disaster could make life on Earth impossible. If we can't live here, where will we go? I'm Dr. Basil Singer, physicist and robot builder. I'm on a mission to find a new home for the human race.
Imagine doing this with a spacesuit on.
I'll look at the best science on Earth to work out where in space we could live, and what dangers and adventures lie ahead for the space pioneers.
Guidance is internal. 12, 11, 10, 9. Ignition sequence start.
The brave crew on this mission to Mercury will begin their adventure in the biggest rocket ever built.
And liftoff.
We have liftoff for the first manned journey to Mercury.
Program response is good.
It's a daring trip in, towards the Sun, to the smallest planet in the solar system, Mercury. Stunning beauty and unlimited energy awaits us, if we can get there.
It's tougher to get to Mercury than it is to get a spacecraft completely out of the solar system.
And when we do land, we'll endure the greatest temperature range of any planet in the solar system.
Mercury is kind of a world of fire and ice.
To the cold side of Mercury. Here we come.
I'll be meeting the visionaries who believe every downside of Mercury can be turned to our advantage.
You might be able to make a habitat on big wheels and just keep going around and around.
We're on a mission to tame the angriest planet in the solar system. This is my data command center, where I'm pulling together everything I need to plan an assault on Mercury. From here, I'll discover that success or failure hinges on one huge challenge: coping with the godfather of the solar system, the Sun. Every aspect of getting to Mercury, landing there, and surviving there is in the hands of its fiery neighbor.
If you were to be on the surface of Mercury and look in that direction, as difficult as it might be, the sun would be 3 times bigger across. That means it would have 10 times the amount of illumination coming down.
All that sunlight heats Mercury's surface to 800 degrees Fahrenheit. Mercury is such a tough place that not even a robot spacecraft has landed there. In 2011, NASA's Messenger spacecraft will enter the nearly as harsh environment of Mercury orbit. It'll go through pain no ship has felt before. This mission is a vital source of clues for my Mercury crew. Every component on Messenger has had to endure a session in the solar chamber. I've come to Johns Hopkins University in Baltimore to see what 10 times sunlight can do. First, I want to have a go myself, but there are conditions.
All right, Andy. Can you turn the light on, please?
Stand off-center and wear full ultraviolet protection. Wow, seriously bright, but the danger is in what you can't see. On Mercury, heat radiation, or infrared, and deadly ultraviolet are also 10 times stronger than on Earth. Together, they can give you fatal burns, blind you, and cause cancer. Time to turn up the beam and find out how it'll affect my Pioneer's spacecraft. I've brought along a solar-powered fan to act as my guinea pig.
All it is a very simple solar cell with some plastic optics, and the solar cell's connected directly to this small motor which is going to spin this fan.
The first test mimics solar intensity just outside our atmosphere.
All right.
Right, let's turn on the sunlight.
Okay.
That button again.
Dowser.
Starting at a low intensity. There you go. What intensity are we at now? We're about...
We're running like less than 30.
So you're about 25%, a quarter of normal solar intensity.
That's correct.
Right. Can we crank that up to 100%?
Yes, we can.
I wanted to test a solar cell because the intense Mercury sunshine should be a great source of electrical energy. But silicon solar cells like mine and the ones on most spacecraft have a problem. They like light, but they don't like too much heat.
Right, we're coming up to, look, 88, almost 90 degrees Celsius, which is about 150, 160 degrees Fahrenheit.
That's correct.
It's getting pretty hot now,
Yes.
and it's still okay.
I see some kind of warpage here, maybe.
Yeah?
The mounting of my solar-powered motor is melting and smoking.
The black plastic looks kind of wet. And it's barely hanging on in there.
But the solar cells themselves are loving the constant power.
Way above 200 degrees Fahrenheit, and this is starting to warp in a major way.
Yes.
Time to ramp up to Mercury level. This means fitting a beam concentrator between the light and the chamber.
Right, motor still running. Let's whack up that intensity. So now you think 100% relative intensity is equivalent to how many suns?
It could be 5, 6.
But with that lens in place, it's much more intense than it was before.
Many more suns, yes.
We're not even at Mercury strength sunlight, but my silicon solar cell is already weakening.
Oh,
Yep.
it stopped. So this has stopped working, and we're only at 150, 160 degrees Celsius now, whereas on the surface of Mercury, it's more like 400 degrees Celsius.
Let's see what we have.
This could be a disaster.
It's not so much functional anymore as a piece of artwork.
Yes.
If we fit solar panels like these to our ship going to Mercury, we'll be in big trouble. The guys at Johns Hopkins spotted the same problem, so they've invented a neat workaround for Messenger's solar panels. 2/3 of the silicon cells are stripped away and replaced by mirrors, which will deflect most of the sunlight. The rear of the panel then works like a radiator, getting rid of heat and cooling the remaining cells. This system works fine, as long as you keep the radiators pointing away from the sun. Otherwise, the solar cells will fry. Our Mercury spacecraft with its solar panels must be kept facing in the right direction. But surviving the sunlight is only the first challenge facing the pioneers. The plan is to land, and that means choosing a safe landing site. They'll have to pick carefully because Mercury's surface is littered with the consequences of a violent past. One feature stands out as somewhere human settlers would be keen to explore: Caloris Crater.
It's just an enormous crater, really, that was formed when some very large asteroid or comet struck Mercury a long time ago.
The Caloris Crater has intrigued scientists since a blurry image taken by Mariner in the 1970s. At 1,000 miles across, imagine a crater that stretched from New York to Miami and is itself pitted and scarred by newer craters. In 2008, Messenger's camera captured a geological puzzle hiding within its huge expanse.
Well, the feature in the middle of the Caloris Basin, which has been informally named the Spider, is a large radial complex of flat-floored troughs. There are maybe up to 100 of these troughs, and they radiate out from the centre. It's very unusual. We've seen a lot of impact basins throughout the solar system. We've never seen anything like this before.
Mercury is a world shaped by impacts, and an impact probably formed the Spider, with dramatic consequences. When a big asteroid hit the floor of the Caloris Basin, it pushed it down. Then the floor bounced back up again, stretching the ground to breaking point. Then the canyons were pulled apart, and the ground dropped away. The Spider was born. Weird geological events like these have created a treacherous landscape, dangerous to land on and tough to navigate. So any thoughts of a day trip to the Spider are a long way off. As the Pioneers sleep, no one has noticed that the spacecraft is slowly rotating. The radiator panels, meant to face away from the sun, are about to feel the full force of the solar glare. Situation critical. The first solar cells would burn out in just 120 seconds. As the crew sleeps, their ship is drifting. The unshielded radiators now face the sun. The solar cells begin to fry. 45 million miles away, Mission Control detects the error. Jolted from sleep, the Pioneers are quickly back on track, but it was a close call. Mercury's a really small target next to a very big, hot enemy. It's so close to the sun that it's hard to see Mercury at all. The odds are stacked against the crew even getting there.
It's tougher to get to Mercury than it is to get a spacecraft completely out of the solar system. Mercury is the twerp of the planets. It's the smallest, so it doesn't have enough mass to slow the spacecraft down when it gets there. It doesn't have an atmosphere, so you can't come in and use the atmospheric effects to drag on the spacecraft and slow it down. But by far the most important effect is that it's closest to the sun.
Ignition sequence start. 6.
It all adds up to a task that at one time NASA thought was impossible. The journey to Mercury is a two-part process. First, you have to fight gravity, lift off from Earth and get into space, and for that, you need a big chemical rocket. Then from Earth orbit, you have to reach Mercury. But that needs a huge amount of energy, so much that a conventional rocket couldn't cope.
The rocket would be so big that it would be impractical, and so people have to look at other ways of getting to Mercury.
I need a power plant with the guts to get all the way to Mercury, but light enough that we can actually get it off Earth. At the Jet Propulsion Laboratory in Pasadena, they've come up with a radical way to do that. A rocket powered by electricity. It's time to fire up the engine.
Hi Basil, pleased to meet you.
Nice to meet you.
He's operating it from this computer, which controls these power supplies that actually provide the power to the thruster.
Right.
Steve, would you start the thruster for us?
Sure.
That's it.
That's it.
Simple.
Thrust is on.
That's the thing about electric propulsion. It's got none of the rock and roll of a normal rocket. Ion engines work in a completely different way to any propulsion system used before. They use electricity from solar cells to accelerate gas particles out of the back to generate the thrust. As each particle leaves the back of the spacecraft, it gives the ship a tiny push the other way.
That is a big vacuum chamber. So you're trying to recreate conditions, space-like conditions.
That's exactly right.
Yeah.
You're trying to make it just like space, so we can test how the engine works and how long it lasts. What you want to do is throw things out as fast as you can, so you get more push from each little bit of propellant that you spit out.
Can I see the engine?
Sure. If you look through this window, you can see the engine. It'll have a very bright blue glow.
To be honest, it isn't all that impressive. I've been promised an engine that will outperform a conventional rocket, but it certainly isn't spectacular. But what's amazing about iron engines is that when they burn, they just keep on going. Normal rocket engines develop millions of pounds of thrust, but they only burn for minutes. Iron engines don't do the fireworks, but they run for years and years, and that makes them revolutionary. John's engines have run continuously for 3.5 years and are designed for much longer. If you do the math, it turns out that for the same weight of fuel, an iron engine will do 10 times the work of a conventional engine.
This is basically the ultimate in green propulsion systems because it uses an inert gas. It's solar powered, and it looks pretty.
But any spaceship captain will choose an iron engine with a heavy heart. When they arrive at Mercury, the pioneers must be going slow enough to drop into the planet's orbit. If they arrive at the wrong speed, they won't have the instant power of an old-fashioned engine to get them out of trouble. Instead of landing, they could be heading for empty space, or worse, into the sun. But there is a way around this. We can get some free power from the planets.
The smart way of doing it, of course, is to take advantage of the Earth's gravity field, the gravity field of Venus, and the gravity field of Mercury. So you use the planets that Mother Nature has provided for us.
And here's how. The spaceship uses the gravitational pull of a nearby planet to get to previously unreachable destinations. Gravity assists can be used to speed them up, or in our case, slow them down. I wanted to get my head around how gravity assists could help my pioneering spacecraft hit just the right speed to drop perfectly into Mercury orbit. So I've built my own inner solar system. The tiny steel ball is the Pioneer's spacecraft, and I'm launching it out across the solar system. With no gravity assist, this is the route that it takes. But when we pass really close by the huge mass of a planet, something interesting happens. In my solar system, this magnet is Venus. And if I get the timing exactly right, the pull of Venus actually slows the spacecraft down and makes it drop into Mercury's orbit.
And here comes our spacecraft that's trying to get inside the orbit of Venus to Mercury's orbit. We want to decrease the orbital energy. We're going to do a front-side pass of Venus, and here, as it goes by, Venus, so much larger than our little spacecraft, is going to give it a kick this way. So by doing that time and time again, we can actually use Earth, Venus, and Mercury to reduce the orbital energy of our spacecraft until it's the same orbital energy as the planet Mercury. And so that's the smart way of doing it.
After 6 years under electric power, the explorers face a do-or-die maneuver of fine braking to drop into Mercury's orbit. But they're nervous. They must arrive at Mercury at exactly the right position and speed. The cost of failure is high. Skipping out into space or a fiery death in the sun. the pioneers heading for Mercury face the most critical moment of their voyage, orbit insertion. As the captain hits the button, they keep an eye on their position. Success! They are one step closer to a walk on the fire and ice planet. The hardest part of getting to Mercury has now been achieved. In low orbit around the planet, the space pioneers enjoy a view no humans have ever had. They face a critical choice. With a whole planet to choose from, where should they land? I'm at the Applied Physics Laboratory at Johns Hopkins University, home of the Messenger mission to Mercury. They can tell me what the main sites are like and what dangers might confront our explorers.
You'd have to take a lot of care if you were landing on the surface of Mercury. It's extremely rugged. The whole surface is covered with impact craters and huge tectonic features like cliffs that can go for hundreds and hundreds of kilometers. So you would have a hard time, I think, finding a smooth, flat area to land on.
And I can see what she means. This is the most dramatic of Mercury's giant cliffs, Discovery Scarp. It's over half a mile high and 400 miles long. It's not a great place to land. Finding somewhere flat on Mercury is going to be a major challenge. Louise is investigating effects of impacts on Mercury, and she's discovered it's a dangerous place for our pioneers to live. Because it's such a small planet, big impacts don't just affect the area where they land.
You see that plume of smoke coming up?
I do see that.
Dust coming up in the middle.
An impact of that size would have a huge effect on the whole of Mercury, and actually we think that the shock waves from the Caloris impact went all the way around the planet and interfered with each other as they came back round on the other side. And we see some terrain that's been called the weird terrain on the antipodal part, so right opposite Caloris on the other side of the planet.
Finding a flat landing place is the first problem. The next is to find a site that offers protection from Mercury's extremes of hot and cold. Louise has an idea.
If you wanted to set up a base there, you might consider going to the poles, where at least you have a little more control over how much sunlight you get on each part of the Mercury orbit.
Unlike the Earth, Mercury's North Pole always points straight up. Up here, the sun is always on the horizon, making it permanently dawn or dusk. A crater near the pole could be a great place to live. The sun barely catches the crater rim and never reaches any lower. A base camp here would always be protected from the sun's heat and radiation. And there's another reason to head north, an accidental discovery made in the 1990s. Because Mercury is so hard to see from Earth, astronomers turned to radar. Using the giant Goldstone and Arecibo dishes, they bounced radio waves off of the tiny planet. The resulting pictures contained a shock.
It was very surprising when radar astronomers discovered that Mercury has ice at its poles, large patches of ice.
The presence of water, even frozen water, on this barren landscape is great news for my mission. The crew will live under the protective rim of a crater at the North Pole, shielded from the sun's heat and deadly radiation. Above the rim, the sun will provide power. Below, a supply of water. In this oasis, the temperatures will be similar to those in the Antarctic. This offers the exciting possibility of exploring Mercury on foot. But despite Earth-like temperatures, walking around will feel very different from at home. Mercury's got a third of the gravity on Earth, and that'll have a really big effect on the human body. My mission is to find out how the Mercury settlers can enjoy maximum mobility with minimum exertion.
If you have to exert a lot of energy to do a given task, you can't stay out very long. If you can lower your metabolic rate, if you can operate more efficiently, then you can stay out a much longer time.
Chris Carr specializes in working out how differing gravity affects the way we walk. He's got an amazing device which will let me experience walking anywhere in the solar system without leaving his lab.
So what we have right here, we have the adult version of the baby bouncer. So let's give it a try. Go ahead and step forward just a little bit. And we'll bring this down.
This is a variable gravity treadmill and works by partially supporting my weight to let me walk in non-Earth gravities.
So we're going to take you probably first to close to lunar gravity.
Chris sets the equipment so I weigh what I would on the moon.
Houston, Apollo 11, Star 40 has just disappeared now. Lights on, picking up some dust. 30 seconds, over. Okay, engine stop.
The moon is the only low-G environment where man has ever walked. So maybe the space pioneers can learn from the Apollo guys.
If you don't mind, you can step on there, and this will just tell us about what we're aiming for.
165.
So somewhere in the low 20s is going to be a good estimate.
Yeah, okay.
We're ready to go. The load on my legs is now equivalent to walking on the moon.
Here we are at 2 miles per hour. And try jumping a little bit. And there's 2.5 miles per hour.
Right, so it's kind of like running. I can run, but it's the frequency that I'm stepping is much less.
It's clear that the basics of mobility change dramatically when we reduce gravity by this much. 3 miles per hour on Earth is walking pace, but that's not the case on the moon.
At this speed, it's more efficient for me to run or bounce like this.
At this gravity, in fact, it's going to be more efficient per unit distance for you to run or lope to get somewhere than to walk.
What's it, loping?
Loping.
Okay.
It's like a skip, but without changing which foot you're bouncing on. Give it a try if you'd like. Let's try that. Wouldn't mind hopping on there.
Well, the same principles of movement apply when we swap from the 1/6 Earth gravity found on the moon to the 1/3 gravity on Mercury.
Let's try walking. What do you think?
Yeah, I think walking
Pretty
would be all
comfortable?
right. Yeah.
Walking's all right? How about jumping?
My feet, when I land, on the moon, they touch almost at the same time, but here, one comes quite a bit after the other.
Okay. And how does it feel in terms of, you know, how much work it is to do?
Okay, this is running, and I'm feeling quite light and bouncy, and it doesn't feel that difficult. Right, loping. I'd say running was easier.
Loping seemed the most efficient way to get around on the moon, but on Mercury, I'd definitely rather be running. This is an important piece of intelligence for the Mercury pioneers, because in this ultra-harsh place, being able to move around quickly will be a matter of life and death. Mercury is packed with spectacular sights to explore, like the 1,000-mile Calorus Basin. And Discovery scarps 400 miles of spectacular cliffs. But all these sites are off limits, as they're too far from the shelter of the polar region. However, some Mercury scientists think there might be a way to explore anywhere we like.
Another idea is if you could go right on the terminator, right at the line between the hot side and the cold side, that might be a place that you could survive for a while.
On one side of Mercury is extreme heat. On the other side, deadly cold. Mercury spins incredibly slowly on its axis. one day on Mercury lasts a staggering 176 Earth days. The result is that pioneers will be exposed to long periods of deep chill, followed by months in the full glare of the sun. But what if there was somewhere between the two extremes? An area where the temperature is just right. This is the twilight zone, where night meets day, and experts have named it the Terminator. I need to discover how wide the comfort zone would be within the Terminator to find out the limits of where my pioneers can survive. I'm on what I suspect will be a very uncomfortable fact-finding mission.
Okay, Basil, so what we're doing now is we're going to experience what happens if you move towards the edges of that thermocomfort zone that you've got on Mercury.
Mike Tipton is an extreme survival specialist. He's got a two-part test planned for me to see what happens when my body gets to the limits of hot and cold.
Now that camera there is looking at my thermal signature before I go in.
Yeah.
And it's all quite bright. That means I'm hot.
It does. If you concentrate particularly on your hands there with the face in between them, and you're controlling your deep body temperature at the moment just by changing the amount of blood that goes to the skin. You're not having to sweat and you're not having to shiver.
Right, to the cold side of Mercury.
To the cold side of Mercury. Here we come.
This room is as cold as a home chest freezer. It doesn't take long for the extremities of my body to start suffering.
How cold is my skin now?
Now you've come down from your starting temperature. You're down by about 20 degrees Fahrenheit already.
Wow. Now, we've only been in here for 4 minutes and 15 seconds.
Yeah.
And the blood flow to my extremities is being shut down.
Yeah.
5 minutes later, and the Arctic temperatures are really starting to take their toll. Even though I look okay, I'm now losing heat faster than my body can generate it.
Your extremities are becoming cold and they've reached the level where we, for safety reasons, withdraw you from the environment.
It's starting to get painful.
Yeah, let's go.
Okay.
I'm now at the cold edge of my survival zone, 36 below. But what about my upper limit? Walking this corridor is a bit like crossing Mercury's Terminator zone. From night to day.
Are you ready to go and experience the hot side of the band? Okay then, Basil, let's get into position.
That is hot.
Yep. Start the timer. We're just going to do some light exercise in here.
In here, it's as hot as Death Valley in July. And I can tell you, even light exercise in 120 degrees Fahrenheit isn't fun.
Clammy, I'm sweating all over.
I'm not sure I can keep this up for much longer. For the settlers on the Mercury Terminator, this temperature would be at the very edge of their tolerance levels.
When you get up to a deep body temperature of 113 degrees Fahrenheit, the proteins in your body will start to denature. In the same way as when you fry an egg and it gets hot, it goes white. And you're essentially now moving into a situation of hypothermia and hypothermic death. It's time to get you out back into the cool environment outside.
Okay.
Well done.
That sets the upper comfort limit at 122 degrees. And I know that 36 below freezing is my lower limit. So what does this equate to in Mercury's Terminator zone? Because Mercury has no insulating atmosphere, as night falls, the temperature drops incredibly quickly, from 800 to minus 300 Fahrenheit. Jeff Landis has worked out that the human comfort zone is just 30 miles wide. However, Mercury is rotating, so the Terminator line is constantly on the move. Earth has a Terminator too, but our line moves at 1,000 miles an hour.
Well, Mercury rotates a little bit more slowly than Earth, fortunately. So if you could just chase the Terminator, you'd only have to move about 2 miles an hour to keep up with the sunset. You might be able to make a habitat on big wheels and just keep going around and around so that you always have that solar energy, but you're also always at the area that isn't too hot.
Jeff's genius solution takes advantage of Mercury's sunshine and shade. A huge rolling habitat will stay in the cool zone of the Terminator. Following behind in the sunlight is their power station, a small truck that turns sunlight into electricity. This extraordinary home on wheels can keep going forever, circling the planet every 176 days. Rolling forwards at 2 miles per hour, the pioneers have traveled miles from their cool crater base. But something's wrong. They're using oxygen far faster than expected. Reserve supplies back at base are more than a week away. Away from base in their slow-moving habitat, the pioneers are running out of oxygen. They need to find oxygen on Mercury, and fast. No planet or moon found so far has a breathable atmosphere, and space missions can't carry more than a few months' oxygen supply with them. Permanent settlement will be impossible unless they can work out how to make oxygen from the materials they find around them. A crack team is right now working out how we could do this on Mercury's lookalike, the Moon. The Moon is covered in dusty dirt called regolith.
Although the surface appears to be very, very fine-grained as you get close to it, it's almost like a powder.
This powder is the result of the surface being smashed up by billions of micrometeorites, tiny rocks from space traveling at high speed. Mercury has come in for the same punishment, because it also has virtually no atmosphere to halt these miniature missiles. Day one on an experiment that could move forward space exploration by one giant leap. All eyes are on the world's biggest box of moon dust.
We have soil in here, it looks like sand, and the important thing is we know its density, we know its cohesion, we know it's how the dirt flows over the tool.
So this is the best stuff we got on Earth to simulate what kind of dust there is on the moon.
This is the best stuff we have of this quantity today.
Moon dust is really bad news. It ruins equipment because it's so fine and abrasive. But when researchers analysed the dust, they were amazed. It contained lots of oxygen. This got scientists wondering, can we somehow harvest moon dust and then turn it into air that we can breathe? Diane's challenge is to plan the logistics of setting up an oxygen factory on the moon. Job one is to collect the dirt. It turns out that digging on the moon isn't as easy as you might think.
On Earth, mass is no object. When you dig into the dirt, you need a reaction force. And so what they do on Earth is they give you a really big multi-ton excavation vehicle.
Yeah.
To resist the force of digging into the dirt.
Right, you're talking about Newton's third law, action and reaction. If I push down on the dirt pushes back on me.
Exactly.
You can't do that on the moon because there's less gravity. You just go up in the air.
This digging experiment is geared towards collecting the exact amount of moon dust a crew will need to survive there.
Now that amount, how many times a day would you have to pick that amount up?
We would need 2 of these loads a day.
2 of these loads a day?
Yes.
And how many astronauts could that sustain?
That's about what we would need for a permanent crew of 4 to 6 on the moon.
2 scoops like that every day could keep 4 to 6 astronauts with enough oxygen.
Yes.
That's amazing.
Here's how it might work on Mercury. Twice a day, pioneers dig a load of regolith and tip it into a small chemical plant. NASA have proved that it works. They've made oxygen from rock in a test experiment on Hawaii. Digging dirt won't be the most exciting thing the Mercury settlers do, but it might be the most important. The pioneers now know that they can conquer the worst Mercury can throw at them. They enjoy Earth-like temperatures, a mobile habitat, water to drink, and now air to breathe. Of course, life won't be easy, but I've discovered the intense sunlight might not be all bad news. It offers the chance to try a technology that has, until recently, been the stuff of science fiction. These huge sheets of metallized plastic are being crafted into solar sails.
Solar sail is exactly as its name implies. It's a sail, but instead of wind pushing on it, it's sunlight pushing on it. And as light reflects from the sail, it transfers that momentum to the sail and causes it to move through space.
The force of sunlight is real, but unbelievably weak. To propel a spaceship forward, solar sails will have to be incredibly lightweight and absolutely huge.
If you deploy a large solar sail, one, 600 miles to 1,000 miles in diameter, inside the orbit of Mercury, you get a lot of sunlight falling on a big lightweight sail. You're going to accelerate it very, very rapidly toward the outer edge of the solar system.
The bigger you make a sail, the faster it will go. For now, the challenge is how you make the sail, pack it into a rocket, and then get it to unfurl perfectly in space. Many scientists believe that solar sails are the only technology that can be scaled up enough to take us to another solar system. And chances are, it will have been launched at Mercury.
If we get inside of Mercury, or inside Mercury's orbit, you can get as much as 16 times as much thrust as you get if you deploy the sail here at the Earth. So if you want to go really, really fast, the key is going to be to deploy your sail as close to the sun as possible to take advantage of all that extra sunlight to get all that extra kick to get your sail moving.
When I first started investigating Mercury, it seemed like a really unpromising place to live. Extremes of heat, cold, and radiation make it incredibly inhospitable. But with imaginative technology and Mercury's natural resources, one day it will be possible to live here. And when mankind begins to explore new worlds around distant suns, their ships could fuel up at Mercury's interstellar gas station.
Even at 3.5 miles an hour, do you feel like you're working a lot harder or
running
a little harder?
Isn't very comfortable like that. That's much easier. Can I look directly down the tube as well if I want?
Yes, you have your glasses on.
It's really bright.
You could dig a coffee cup of dirt once a minute for 8 months, and you would have enough dirt.
Coming down.
All that sunlight heats Mercury's surface to 800 degrees Fahrenheit. Mercury is such a tough place that not even a robot spacecraft has landed there. In 2011, NASA's Messenger spacecraft will enter the nearly as harsh environment of Mercury orbit. It'll go through pain no ship has felt before. This mission is a vital source of clues for my Mercury crew. Every component on Messenger has had to endure a session in the solar chamber. I've come to Johns Hopkins University in Baltimore to see what 10 times sunlight can do. First, I want to have a go myself, but there are conditions.
All right, Andy, can you turn the light on, please?
Stand off-centre and wear full ultraviolet protection. Wow, seriously bright, but the danger is in what you can't see. On Mercury, heat radiation or infrared and deadly ultraviolet are also 10 times stronger than on Earth. Together, they can give you fatal burns, blind you, and cause cancer. Time to turn up the beam and find out how it'll affect my Pioneer's spacecraft. Themselves are loving the constant power.
Way above 200 degrees Fahrenheit, and this is starting to warp in a major way.
Yes.
Time to ramp up to Mercury level. This means fitting a beam concentrator between the light and the chamber.
Right, motor still running. Let's whack up that intensity. So now you think 100% relative intensity is equivalent to how many suns?
It could be 5, 6.
But with that lens in place, it's much more intense than it was before.
Many more suns, yes.
We're not even at Mercury strength sunlight, but my silicon solar cell is already weakening.
Oh, It stopped. So this has stopped working, and we're only at 150, 160 degrees Celsius now, whereas on the surface of Mercury, it's more like 400 degrees Celsius.
Let's see what we have.
This could be a disaster.
It's not so much functional anymore as a piece of artwork.
Yes.
If we fit solar panels like these to our ship going to Mercury, we'll be in big trouble. The guys at Johns Hopkins spotted the same problem, so they've invented a neat workaround for Messenger's solar panels. 2/3 of the silicon cells are stripped away and replaced by Mercury. Stunning beauty and unlimited energy awaits us, if we can get there.
It's tougher to get to Mercury than it is to get a spacecraft completely out of the solar system.
And when we do land, we'll endure the greatest temperature range of any planet in the solar system.
Mercury is kind of a world of fire and ice.
To the cold side of Mercury. Here we come.
I'll be meeting the visionaries who believe every downside of Mercury can be turned to our advantage.
You might be able to make a habitat on big wheels and just keep going around and around.
We're on a mission to tame the angriest planet in the solar system. This is my data command center, where I'm pulling together everything I need to plan an assault on Mercury. From here, I'll discover that success or failure hinges on one huge challenge: coping with the godfather of the solar system, the sun. Every aspect of getting to Mercury, landing there, and surviving there is in the hands of its fiery neighbor.
If you were to be on the surface of Mercury and look in that direction, as difficult as it might be, the sun would be 3 times bigger across. That means it would have 10 times the amount of illumination.
Our planet may be under threat. One day, a natural or man-made disaster could make life on Earth impossible. If we can't live here, where will we go? I'm Dr. Basil Singer, physicist and robot builder. I'm on a mission to find a new home for the human race.
Imagine doing this with a spacesuit on.
I'll look at the best science on Earth to work out where in space we could live, and what dangers and adventures lie ahead for the space pioneers.
Guys,
Guidance is internal. 12, 11, 10, 9. Ignition sequence start.
The brave crew on this mission to Mercury will begin their adventure in the biggest rocket ever built.
And liftoff.
We have liftoff for the first manned journey to Mercury.
Program response is good.
It's a daring trip in, towards the sun, to the smallest planet in the solar system. I've brought along a solar-powered fan to act as my guinea pig.
All it is a very simple solar cell with some plastic optics, and the solar cell's connected directly to this small motor which is going to spin this fan.
The first test mimics solar intensity just outside our atmosphere.
All right.
Right, let's turn on the sunlight.
Okay.
That button again.
Dowser.
Starting at a low intensity. There you go. What intensity are we at now? We're about
running like less than 30.
So you're about 25%, a quarter of normal solar intensity.
That's correct.
Right. Can we crank that up to 100%?
Yes, we can.
I wanted to test a solar cell because the intense Mercury sunshine should be a great source of electrical energy. But silicon solar cells like mine and the ones on most spacecraft have a problem. They like light, but they don't like too much heat.
Right, we're coming up to, look, 88, almost 90 degrees Celsius, which is about 150, 160 degrees Fahrenheit.
That's correct.
It's getting pretty hot now.
Yes.
And it's still okay.
I see some kind of warpage here, maybe.
Yeah?
The mounting of my solar-powered motor is melting and smoking.
The black plastic looks kind of wet. And it's barely hanging on in there.
But the solar cells